Okay, we're here. Sorry for the slightly late start, but we actually have video now. Yeah. And we did not have video moments ago. So we're back. We're good. How are people doing? How are games coming along? Progress?
Yeah, we're getting something.
Good. So schedule is worth going over because there's a lot coming up in a very short period of time for the class. So we have the first game due on Sunday. So make sure that you're making as much progress as you can ahead of our meetings on Friday. Friday meetings this week, I really want to just I want to be able to play test what you plan to submit or as close as you can have to what you plan to submit so that I can help you figure out how to best utilize your last couple of days. We have an exam a week from Wednesday. So I owe you a study guide by Wednesday. We have already finished. I've made sure to look at what was on that study guide where I historically cut this curriculum. We've already passed that point, just barely. So we're good. My plan for this week then is I want to lecture today, and then I want to give people a little bit more time this week to, since this is right by the time the game is due, work on their games a bit during the next couple of days. And I plan to try to help you get unstuck. When I've said this in the past, people haven't really attended much those couple of days. So I would really appreciate if we can up the attendance so that this is time that you have that you can work together. It's not time that's meant to let you catch up on other things and then eventually get to this. But I'd like to see more people in those sessions. Next week, we have our game reviews. So after the game is submitted on Sunday, you will receive 4 games worth of games you didn't make, and you'll need to write reviews for those games. You'll need to play each game for half an hour, and the grade outcome for that, when I'm grading the reviews themselves, will be based on the extent to which you rope in material from last quarter. So I'm looking for an in-depth analysis of the game's design. This shouldn't just be written from the player's perspective. It should be written from a player's perspective who understands design. So analyze everyone's design decisions and how it led to the emergent gameplay that you experienced. So I'm looking for depth. If you just say this mechanic was fun because dopamine, or this mechanic wasn't fun because it was frustrating, I'm looking for a lot more depth when you say things like this. Why is that? Dive into the design decisions for why you felt what you felt. So I am really looking for that kind of breakdown for you to understand why you experience what you experience when you play a game that somebody else designed. I'll also talk a little bit about those reviews as we get a little closer to writing those. I want to go over what a good review looks like, what a bad review looks like in terms of writing, depth, quality. I have a couple of examples of that prepared, but that's what we're planning to do. On that Wednesday, we'll take that exam. I anticipate spending some of next Monday and Tuesday preparing for that exam, so there will be at least one review session in here before the exam. Then we will, after our Friday lab, have an evening game experience. I'm going to send out an email to the entire undergrad and grad mailing lists, inviting professors and students to come play our games. If you can coordinate within your groups, I would like at least one person from each group to be able to be here for the duration of that event. Usually this lasts from something like 4 to 7 or 4 to 8 p.m., depending on people's interest. It doesn't have to be the same person there the entire time. You can rotate out, but I would like someone to be here to talk about the development of your game, answer people's questions about it, talk about the design decisions as people are playing it. And that is another way that you can get feedback from people, is watching blind playthroughs of people playing your game. That's a very rewarding and motivating thing to go through. So I highly recommend being present for that. There's no grade item associated with it, but I will be bringing food. So hopefully that by itself makes it a little bit more worth your time.
The Friday of next week.
Yeah, that's a week from this Friday. So if you have any friends that you'd like to invite, they don't have to be students here. We'll just host the event, or they don't have to be in this class or have taken a class at the Catalyst building yet, or I want this to be as open and accessible to people as possible because your games are awesome and they deserve to be seen and played by people. Not just the people in this class who are reviewing it, but in general, the public. Any questions about the next couple of weeks in here or what that's going to look like? Deadlines, calendar. I will get up the current set of slides for those who want to get started with going over that ahead of next Wednesday's exam. Again, I'll give you a study guide by Wednesday for sure. And other than that, we can dive back into a little bit of reinforcement learning. So again, tomorrow and Wednesday, we'll have a little bit more work time. But I'll try to be a little bit more helpful than I have been in treating it kind of like a social time. But I'll make sure to get around to each group and ask how things are going. All right, last time we were talking about Monte Carlo, and we had a couple of possibilities for how we could handle policy at this point. So there were the two different ways where we could incorporate a behavior policy or not incorporate a behavior policy, which led us to this concept of either on policy or off policy. Regardless, there's a target policy that we are learning, but on policy is going to build the exploration directly into the policy. And off policy is going to separate this into a new policy. We have two policies, one of which is the one we make decisions based on, and one of them is what we are learning from that experience. Think about putting the mind of a 50-year-old adult in the body of a 20-year-old, and you get the idea of how off-policy learning works. The 20-year-old is making silly mistakes, and the 50-year-old is analyzing, thinking, I would never have done that, but because you did that, I'm going to learn something about how I operate based on this ridiculousness that I never would have done. As 20-year-olds, I'm sure you all very much appreciate that. I wouldn't do that. I know you all better. Does that make sense to people? Again, that concept of on policy or off policy. Where is the exploration? Is it built into the one policy we're using, or is it a second policy? We then went into the concept of, we talked about exploring starts, where that is one way to build exploration into the policy. So in that case, you would want an on-policy approach with exploring starts being the exploration part of it. Then we talked about importance sampling, the idea of the ratio between how likely a sequence of events were between these two policies. So now we're assuming we're in an off-policy environment. If that's the case, then how likely is the sequence of moves that we saw given the behavior policy that generated this sequence and the target policy that it's trying to learn about? So we need to convert between those two. We found that we could convert between the two very easily. It just gives us this ratio. This is very complicated math for just telling us that there is a ratio between the likelihoods of these paths. But that is what we found. We talked about this playground very briefly with regards to whether we could go right and terminate the episode or left. 10% of the time we terminate the episode and get a positive reward. 90% of the time we get no reward. And we found that the variance here is infinite, meaning that as we use some kind of learning rate to figure this out, we're going to say, what is the value of being in this one starting state? When we make a decision that says we're going to move left 95% of the time, as we see extreme events, something that is unlikely over a large sample, that is going to start biasing our view because we're using a learning rate to learn this. It's going to bias our view of how likely certain events are. When you use a learning rate like this, you become less prone to the stationarity assumption. What I mean by that is you gain the ability to represent problems that change their probabilities underneath the hood because you want to weight more recent examples more than less recent examples if the underlying problem is changing. But if the underlying problem isn't changing, then you want to take a straight average of all of the runs that you've had. If you don't know, then that's why we use that learning rate. And when we see something highly unlikely over a long period of time, it tends to change. We start to think that the underlying problem has changed, when in reality, all we're seeing is an uncommon event, an outlier with regards to the last 10 runs or 100 runs, or just something that is unlikely. We find that that doesn't happen frequently, but when it does, it creates a spike in the error of our view of the value of this state. And this isn't something that converges over time. We can see that because of this infinite potential variance, even deep into these runs, we see these unlikely events, and they tend to skew our understanding of the problem. So we see those events happening far into the future. So to try to handle this and make this less extreme, one thing we can do is use the concept of weighted importance sampling. And if you use weighted importance sampling, now we're placing a weight on this. And as we go deeper and deeper into this, we find that because of the weight changes, as this starts to, again, using kind of a temperature-like parameter, this tends to converge, and we asymptotically get our bias closer and closer to zero. And this process means that while the bias goes to zero, the variance will increase, but at least early on, we don't start out with these wild swings as we're getting enough information to figure out the ballpark that the value of this state is in. And so it looks a lot better early on. And we find that this is exactly what we see early on with weighted importance sampling. We get a much better view of the problem. Our error is not as high until it eventually converges at about 100 episodes. So all weighted importance sampling is trying to do is take that wild swing in that initial data that we get, because we don't have very much data. Every small outlier is going to change the average by a lot because we don't have a lot of history of data. So as we build that history, it's better to, rather than taking the value as it is, start to weight them by averages. So we're going to get closer to the average that we've seen, and that makes sure that the weighted average early on has less error. Does not do a thing in the long run, though, as you see that these eventually converge to the same values. All right, concept of incremental Monte Carlo. So this is how you can see how you might use both the ordinary importance sampling and the weighted importance sampling that we just talked about. So how are we updating the value of a state? If we're using ordinary importance sampling, then the value of a state at time n+1 is the value at time n plus this weighted 1 over n, however many instances we have so far. That's the weight of the next episode. 1 over n times the return that we get at time n minus the value again. So this is basically just changing our view of the expected value of this state. If you're using ordinary importance sampling, all we're doing is just doing that divided by n. And that means that we're weighting the earliest episodes significantly too much because we don't have any other data. When we have one piece of data, we get a second piece of data. That second piece of data has the weight of half of what we've seen so far. So that data is much more important. But if we use weighted importance sampling, then we see that we are having a much larger numerator initially. And that helps us to kind of converge on the data that we are seeing so that one outlier doesn't affect this as much. How are we doing? Questions on at least the overarching idea? We don't need to memorize any of these functions. It's just that if you found yourself looking at something like this in the future, goal with this is to minimize the amount of research time that it would take for you to understand what's going on or why there are you see an algorithm and it has both ordinary importance sampling and weighted importance sampling. If you've seen it before, you know what that means. You can look it up and try to say, why should I choose one over the other? What does that mean? Yeah.
I'm just trying to understand the concept of some of the other symbols because it's W of N and C of N, because I get W of N is probably the weight of this
Yeah.
one. I'm just failing to see what C is in relation to this in terms of what it represents.
Yeah, C at time n plus one is C at time n plus the weight at times n plus one. So this is a value where we're building a weight, kind of a cumulative weight for every episode that we've seen, and how important the current episode is its weight over the sum of all weights that we've seen before.
Okay, that makes more sense.
Yeah. Yeah, rather than just 1 over n, it's as important as 1 over the amount of episodes that we've seen so far, or the amount of data that we've seen so far. We're going to build it into the weight of the sum of all weight that we've seen before.
That makes more sense. What that represents now.
It's a great question. How's everyone else doing? Does the concept make sense? So we can implement this. Again, some basic pseudocode. All we have here is just basically the underlying math. Code up the associated updates, and then surround that with the logic of the data collection for the episode. And that allows us to collect our weighted returns. And if you do this, then it becomes very apparent what the ratio between the likelihoods are. The unbounded variance of the ordinary importance sampling becomes bounded early on. And that makes sure that we don't see wide swings as we see new pieces of data, which is exactly what that variance was getting at. When we see slightly different kinds of data, then our view of the world shifts drastically. That's what high variance is. So we want to reduce that high variance so that as we're collecting that initial data, we don't see wide swings in our error. And this fixes that. So here's our, in general now, off policy Monte Carlo control. This is the control. Control again just tells us how to make the decisions within the episodes. So off policy tells us that we have 2 policies, the target policy that we're learning and the behavior policy that we're following for exploration. Monte Carlo tells that we're learning directly from our experience. We're sampling the large space and we're gathering that data to try to make sense of the world that we're in with the limited amount of data that we're collecting. Then the control for it is general policy iteration that we talked about before. We're just going to have a general policy that we are following, and as we gather enough data, we're going to optimize the policy using exactly the same logic that we've seen before, except that now what we're doing when we make that change is we're backtracking from the state that the episode ended from and back all the way to the beginning. And we're looking at any changes that we would make to any of those states based on the data that we just collected. Does that change our mind about what is optimal? And we make those changes to the target policy. Note that we're not making those changes to the behavior policy because the behavior policy is still going to explore. So it's not changing the underlying way that we're going to collect data. It just changes what we think the best choice is. We're learning about how to make decisions differently once we switch over from training to now demonstrating the knowledge that we've learned. So we take those 2 policies we learn based off the behavior policy. Once we switch over to now an online performance-based environment, then you use the target policy and throw away the behavior policy. Going back up. So you can see here the difference between the target policy pi. This tells us that it's good to move up and right, but not left. And the behavior policy still is going to move in arbitrary directions just in case the left was a small sample mirage, and we want to make sure that we continue to explore that to make sure that it's not a good thing. In fact, moving right from this position is also not a good thing, but we have yet to learn that according to our target policy. We need more experience from the behavior policy to learn that this right move doesn't get us closer to the green square. It gets us closer to the red square without getting us closer to the green square, which is not good. But more repetition of this, we would learn that from this position, it is best to go up. Total off-policy Monte Carlo control pseudocode. We just do what we've done before. This is just general policy iteration. But the update for how the general policy iteration is evaluated is just that this one equation has changed. Everything else stays the same as we have seen before. So as we find with a lot of reinforcement learning, a lot of the algorithms are related to each other. How you generally collect information is either going to be via simulated experience or actual experience or a zoomed out understanding of the entirety of the state space. When we use dynamic programming, we could zoom out and see the entire state space. With Monte Carlo, we don't have that, but we still use the same general policy iteration steps. We just now, instead of being able to think about what happens, now we actually have to simulate what happens in order to get more or better data on what decisions we should be making. Instead of thinking about what we could be doing, we have to actually simulate it out. Because we don't know enough about the environment that we are in. How are we doing? Any questions on that? So Monte Carlo differs from dynamic programming. Well, it kind of uses general policy iteration that we talked about in dynamic programming, but instead of analyzing the state space, we're learning directly from experience, sampling from this very large state space. So we are directly interacting with the model, simulating, focusing on just a subset of states when we need to. We can force our exploration into particular states that allow us to make sure that we're getting experience with the most frequently visited states, with states that we really need more experience with to be able to make good decisions. We can maintain exploration. We need to do that in one of two ways. We either have a separate policy for it. On policy does that within the policy itself, and off policy makes a second policy that does it. If you use off policy, then we need to use that important sampling ratio to figure out how likely a sample run that we make would have happened according to the two policies. And that's just a ratio difference from each other. All right, time for the last big section of this. This is just temporal difference, and I realize I'm not actually in this. Doesn't really matter which one it is, but temporal difference is a slightly different road from Monte Carlo. Just like with Monte Carlo, we're still going to be simulating entire episodes, but unlike Monte Carlo, we are not going to be waiting until the end of the episode to make a change to the set of states that we visited. We're going to make a single move, and then we are going to immediately figure out, based on the value of the state that I reached, I'm going to immediately back propagate that information back to the state I came from. Only then will I make the next move. So you're making single moves at a time and analyzing the value of, I made a move, let's save that and move back. And so you can imagine something like playing a real-time strategy game. And the first decision that you might make is, with my first batch of resources, should I build a standing army or should I build a wall? Should I be more offensive or more defensive? Rather than waiting all the way until the end of the real-time strategy play to figure out whether you won or lost, you could have some measure of how prepared am I at the end of this process. And you could analyze, based on the information that's happened, was I attacked? If I was attacked, then while I'm creating my defense, it's probably better to have had some kind of offense to fight back. But if not, now I will have more time to know when an attack is coming to provide to make a standing army. So I don't need to have quite as big of a standing army if I have my defenses set. So you're making decisions about how good your actions were, but the game hasn't ended yet. The game is still in progress, and you're backtracking to, is it better for me to very early on go offense heavy or defense heavy based on just that? You can imagine that other decisions were made deeper into the game as to why you won or lost. You don't want to propagate all of that back to your initial decision of offense or defense very early on. You could make that decision right away based on some reward function for how good is my standing after I finished creating my offense or my defense. So it's kind of a one-step process. At this stage in our tree, we're making a decision about, based on how good this state is, I can learn something about this state and this action from the fact that I ended up here. Whereas with Monte Carlo, we would be continuing to make decision after decision after decision down to a terminal node and then back propagate all that information through all decisions that were made in the episode. What do we think? Why would we choose one of these or the other? Is there value to one over the other in certain situations? Yeah.
Yeah, I feel like with the example of the real-time strategy, it can take a long time to get to that terminal node and even decide if the route to get there at any input.
Yeah. A lot of it has to do with the underlying assumptions, like how much does this decision influence the next decision? You want to learn with that interaction without worrying about all the noise that is all of the causality that happens later on in the episode. So if you have, there's almost nothing in common between this decision and the next decision. There's no causality to it. Then temporal difference makes a lot of sense. If there is a lot of causality, then Monte Carlo makes a lot of sense because it will embed that decision making kind of at the sequence of steps level. You'll start to make that connection between decisions that you made down here and how it affects up here. But again, if these are completely independent, the reason this lost me the game was this decision. You don't want to assign weight to these decisions up here that were the reason you lost the game was down here. You were in a good position, but then you fumbled. You don't want to learn that setting me up in this position was bad because I lost the game. So let's take a look at how Monte Carlo gets its error and how temporal difference gets its error and how those differ. So Monte Carlo waits until the very end of the episode, and then is going to apply this learning rate to the return for every state that we see and basically say, what is our old return, the average return that we calculated before? What is the value so the return that we get, what is the value of the state that we thought? If there's a difference here, then our episode differed from our expectation by some amount. We're going to learn based on that and update that with the value of as the new value of the state. What that means, you're going to look at an arbitrary decision in your tree of decisions that you made to get to a terminal episode. And when you're looking at this return, there's a value of this state that we expect it to be. Maybe we say that we expect to win from here 80% of the time. And what we found here is that we lost. So the return tells us that the actual reward that we just got from here was 0, but the value of the state that we expected was 0.8. We win 80% of the time from here. So now we're going to update this based on our learning rate that says if our learning rate is every time we see a new episode, we're going to attribute that as 5% of the overall value of the state. We would take this 0.8 and we would subtract the learning rate, 0.05, times the new value that we got. If this return was 0 minus the value of the state, then this is the difference between that is minus 0.8. So we would be taking this value and bumping it down. Saying that because of this loss, we're gonna weight this loss at 5% of our overall experience and weight it down. And that would be true for every one of these nodes. As soon as the episode terminates, notice that we need both the return and the value. The return tells us that we finished the episode. We know what the return was because we know how this episode terminated. That's nowhere in the temporal difference because we're not waiting for the episode to terminate. So in temporal difference, rather than waiting for what happened, we're going to approximate what would have happened by looking at what is the value of the next state. So when we see this occur, we're going to backpropagate this back to that one state. And that state has a value. But here, this state also had a value. When we explore and we end up in this state, we can backtrack now and say, well, when I was in this state and I made some action that got me to this state's value is 0.8. So depending on whether this 0.8 is higher or lower than this state's value, I'm going to move this state's value closer to the value of this state because I just got there. Again, nothing to do with whether we won the game or lost the game this time. We're just looking at the value of this state and immediately pushing it back just one move to say, we got here. Our experience tells us it is this good to be here. So how good is it to be here, given that one more time, we went from here and found ourselves here. So the update is exactly the same update, but this is now based on the temporal difference, the next state that we get to, the value of that state. We use our discount factor here because we would rather end the game faster rather than slower. And then figure out the extent to which that differs from the value of the state. So we're going to add to the existing value of the state some difference between what we expected to happen and what actually happened. But that's just a one move situation. You can imagine yourself playing chess, and in one move, you capture your opponent's queen. That puts you in a much better position than you were before. So you backtrack to the state before you captured the queen, that because I can capture the queen here, that state is also good. And we have more experience now of deciding to capture the queen. So the average value of that state before we did that is good. We don't need to wait until the very end of the game. We just see that this capture is possible and it improves our state. So we're going to backtrack the value of the state after we capture the queen to the state before we capture the queen because we can capture the queen. And we do that for every possible move. If we make a move that puts us in a worse situation, we will backtrack that to the state before that says, according to our behavior policy at least, there was something that we could have done that made us worse. So we're going to drop the value of this state because we experienced that. Questions on that? Does this difference make sense between how Monte Carlo is handling its update and how temporal difference is handling its update? Show of thumbs, maybe? Not getting a ton of feedback. Somewhere between somewhat and okay, what that looked like. For those of you who are kind of more somewhat, anyone want to volunteer and just tell me kind of what you know or what you figured out and what is fuzzy or what don't you understand? A concept in general or just where your confusions are? Yeah.
Monte Carlo waits till the end of the episode, but for temporal difference, if it looks at every single move and says, okay, how valuable is this? Back propagates that.
Yeah.
How does it get that initial value?
That initial value, it's going to take a while to learn. Because the very first time you play a game, you wait until you have a result. But that result only gets back propagated one step. It doesn't go all the way back through the episode. The only state that gets a new value is the one right before you won or lost. then you have to play it again and it will backtrack one more state. And then you'll play it again and it'll backtrack one more state. So it flows from the end of the game back to the beginning of the game. So there is certainly a downside in terms of how long it takes to train a temporal difference model versus a Monte Carlo model. It takes more experience for temporal difference to get closer to an average value. But I will use the next example, a motivating example, to see how the cause and effect will propagate between the system. How long does it take for cause and effect to reach the values of different states? So that's a great point. It does take longer to train. Anything else I can address here? All right, I want to motivate it because this is one of my favorite examples. Here's some pseudocode. Again, this looks exactly like the Monte Carlo prediction, except that we use the temporal difference update here instead of the Monte Carlo update. Other than that, it's exactly the same. But let's look at the driving home example. And the driving home example is very nice. Basically, we're going to have different states of checkpoints on our drive home. We're going to figure out, we leave the office. So there is a state about what time you are leaving your office. You reach your car. How long it takes for you to reach your car will be dependent on the day and the time that you're leaving your office, possibly your weather. There's some kind of consistency with regards to how long it takes you to reach your car. Once you reach your car, the first thing you do is you merge onto the freeway and you go some distance on the freeway and eventually you exit the freeway. So how long does it take for you to go from your car to exiting the freeway? Once you exit the freeway, you get onto a secondary road. How long does it take you to go from exiting the highway to done with the secondary road before you enter your home street? Once you enter your home street, how long does it take for you to arrive home? You can see how there is cause associated with each of these different events. Like, for instance, you can be behind a truck on the secondary road, but because there's so much cause and effect with each of these, do we want the fact that we were stuck behind that truck to affect how long it takes for us to drive the freeway when there are more lanes for passing? Do we want that to affect how long it takes for us to guess on average that it will take for us to get from our cubicle to our car? If we use Monte Carlo, then everything that happened on this drive home is going to be accounted for in the entire time interval that it takes for us to drive home. The fact that it took longer for us to drive home will be attributed to every one of these states that happened before the issue. Whereas with temporal difference, each one of these is going to become a target that we're going to better get a sense of the cause and effect here. So here is the predicted time and actual time in graph form. When we're using Monte Carlo, we look at the actual outcome. It took us 43 minutes to get home. So the estimate when we were leaving our office was that it would take 30 minutes. The Monte Carlo error from these 30 minutes to the actual outcome, that's going to bring this value closer to the actual value, because we have one more data point of taking longer than 30 minutes to get home. So this will be pulled pretty significantly because there's a big error on this leaving the office state. When we reach the reaching car state, because that took longer than we anticipated, now the estimate is that it's going to take us 40 minutes to get home. But because it took us 43 minutes to get home, we're still going to pull that estimate up. But you can see that the baseline we are using for all of this is the actual event, how long it took us to drive home. The fact that a lot of this pull happened at this point, where the estimate of the time was because we were behind a truck, that's pulling all of this up based on this estimate, when the causality is based solely on the issue at the secondary road. So we shouldn't try to make this change. We should look at, did we find a truck on the secondary road? If so, then increase. But you can see how temporal difference accounts for this. When we leave the office, by the time we reach the reaching car, the estimate is 40. So the actual error between leaving office and this value is not based on the entirety of the episode. We look at the estimate for when we reach the car. The fact that we got this one data point that it took us a little bit longer to reach the car than we anticipated is a change in the actual outcome for this, because the actual outcome is the average and not the one piece of data that we had here. So this has small sample issues. And this is going to rely on the target being the average of everything that we've seen in the past. So it tends to, once it starts getting information, it uses that information better. But it takes longer to start getting that information. When we exit the highway, the average is 35 minutes. And the estimate now is going to say that the fact that we were at 40 and then the next one says 35, we're going to bring this down. Which, even though it ended up taking us 43 minutes, the fact that between reaching the car and exiting the highway, that was faster than average. Our highway experience was faster than we otherwise would have expected from leaving. We hadn't gotten behind the truck yet. You can see that our estimate is based solely on the experience we had this time on the freeway. And we're not attributing this to the truck that we got stuck behind. That has nothing to do with. Our speed on the freeway had nothing to do with the fact that we got stuck behind a truck on the secondary road. So we're not accounting for it. Similarly, when we hit that secondary road, we see that we actually bumped that up. That was the reason why it took so long, is that the secondary road took longer than we thought. So we start increasing the highway to secondary road based on that estimate. And we start getting a closer and closer map to what this looks like based on the actual evidence, because these are not related events. Like, there's no cause and effect between those. As soon as there is cause and effect, we probably want to use Monte Carlo. But the fact that there's less cause and effect in this situation tells us that we can model that better by looking at a state by state update rather than an episode by episode update. Questions on this example? So some advantages. Temporal difference. Rather than using dynamic programming, we still don't need the model. We don't need to analyze what the actual underlying state action space. We can still learn directly from our experience, just like we did in Monte Carlo. But versus Monte Carlo, there's online incremental learning. What this means is we're learning during the episode. We don't have to wait for the episode to terminate in order to have any kind of feedback or an idea of how good each of the intermittent states were. If you feel yourself starting to lose an RTS for some reason, this would start to attribute your loss to these middle states when you start to feel bad about it. An online learner using Monte Carlo would have to wait until you've lost. It doesn't matter that you're feeling bad or like you're likely to lose. You're not going to update until you have lost. So that online learning lets you learn from experience before the episode has terminated. And that way, if you find yourself in the not just first visit, but like the multi-visit Monte Carlo, you start learning during that episode before you terminate. You don't have to now worry about first visit versus every visit. You're now just updating one step at a time as you frequently see those states. And that way you could learn from a repeated issue. Like if you're in a real-time strategy game and you make a technological advancement and then run into a brick wall and then get pushed back to the Stone Age and make a technological advancement. And if you have some kind of loop in that regard, temporal difference would be you'd be learning from each one of those and eventually be doing something different in the middle of the episode instead of waiting for you to lose at the end of that process before backtracking all of that through that cause-effect cycle. Monte Carlo needs to ignore episodes with experimental actions. Basically, if you're going to do something that is wildly different from what is optimal, you will learn, yeah, that's not great, but Monte Carlo may still be taking that into account deep in the tree. If we're having initial states in tic-tac-toe, and then we have a wide tree that eventually leads to termination. If we make a bad choice here and end up losing the game, Monte Carlo is going to backtrack all of this to the beginning and make changes to maybe there were some good positions in here that we otherwise, but we're going to eventually need to figure out that this was experimental and we're going to use, if this is off policy, that ratio between the policies to figure out that this was bad. We just use it, which is nice. But just like with Monte Carlo, we guarantee convergence with enough data. We will eventually converge on the true values of each of the states and each of the actions. And we find that in general, it will converge faster than Monte Carlo. Once we start to have some data, then it's able to break apart that cause and effect. It doesn't have to learn the cause and effect embedded within the system. It's able to break that apart and learn them separately, which leads to that faster convergence. We'll give you this example. We don't have a ton of time, so I'll probably introduce it and then we'll come back to it next week. But we start at this middle state C, and we can move left or right. And if we reach the left gray box, the reward that we get, it terminates the episode, we get 0. Reach the right gray box, then we get a reward of 1. So now we have to figure out, okay, how valuable is it to be in each of these different states, A, B, C, D, and E, given that we're going to start with a random policy that's going to move us left or right with equal chance. We can see that the actual true state values for this are, there are only 5 of these states, A, B, C, D, E. So it's 1/6 through 5/6. I'll leave you for a week to think about why that is. Why is the value of this state E 5/6 versus A 1/6? Over a long term, it makes sense that that seems like an average, but why does that work out? Why is that exactly the state's value that it would converge to with enough evidence? Because we're not looking at this system in general. Dynamic programming has us look at this system in general. But with Monte Carlo or temporal difference, you would be relying on the experience that you get playing this randomly. So I'll come back to this and talk about it in a little bit more detail. Gonna leave you with that to think about in the meantime.
Is the test going to come with a full count of 6? Do you anticipate?
Probably not.
Okay.
It probably won't touch anything temporal difference.
Okay.
So through Monte Carlo, you can expect to be on the first exam.
Okay.
And then temporal difference and on, will be on the second.
For the second test, you can like 6 chapters of the book. Is that yeah?
If that happens very quickly, then I'll find something else to talk about. The difference between having a 2.5-hour lecture session that requires breaks and a much better paced 15-minute session that's much more digestible, so we can move a little bit faster through the material.
That makes sense. All right. So you're planning on the second test. What chapters? 6 through
6, 7, 6, 7, 8. I'm not sure exactly what's in those later chapters, but
Okay.
we're gonna get it through temporal difference and a bit of approximation from that.
Yeah,
But that's,
Okay.
there's not too much.
What about